Hello, this is Doug Groom again from Geometrics. This is the fourth session in the Stratagem EH5 training videos. And today we're going to cover the Emage2D MT inversion software. And I'm going to open that up. Now, the Emage2D Inversion software has a very similar interface and features as the previous video, which was the EH5 Pro data processing software. And the first thing we're going to do is open up a data file that was exported from the EH5 Pro. And the Emage2D software will read both .edi files and .eh5 files, both of which can be exported from the EH5 Pro software. So we're going to open up an EH5 data software, and we're going to grab this, which is a profile of 13 different soundings, and open. And as in the EH5 Pro software from the previous recording, the first screen you see is the site location map. And these are the 13 stations. And as in EH5 Pro, you can go to the impedance curves simply by doing a right click or by using the reverse icon at the top. And again, you can do the reverse icon to get the impedance curves of apparent resistivity, impedance phase, etc. And as in the EH5 Pro software, you can do further editing of the apparent resistivities and impedance phases with the same method. Click on the upper left-hand corner for the editing icon, and you can go in there and a single left click will do some additional editing, and you can do phases as well. If you do a double click, it clicks or edit out both the X and Y resistivity or the X and Y impedance phases. And this has already been edited in EH5 Pro, the same sort of thing. You click on the refresh button and it will refresh the screen and show you the changes that have happened in the Bostik, for example. And we can use our back and forth arrows. And same sort of thing, you can do some editing of the phases and of the apparent resistivity. So this is in site number 10, site number 11, and I don't need to go through all of the sites to do editing, but just to show you that those edits are available. 13, 1, 2, etc. And I can refresh the screen after the edits. And if I like, I can go to File, and I can save the EH5 file. But I won't bother doing that at this point. Okay. What I want to do is get into the actual inversion. But first, let's look at the features here, which are the same as in the EH5 Pro software: impedance curves, polars, apparent resistivities, and you can scroll through the different apparent resistivities. You can edit them as previously. You can look at the individual phases, etc. And again, scroll through the phase stations. If you looked at the previous EH5 Pro training, this is all familiar with you. And we can also do an EMAP section of the 13 stations. And as I explained previously, this is not a true TD inversion. It is a 1.5D transform using the 1D Bostic transformations, lining them up along the profile line. This profile is an azimuth of -25 degrees, which would be 339 degrees in a 360-degree compass. And then a smoothing filter applied laterally between the stations. Okay. And there are some additional features in the plot type in the Emage2D software. For example, we can look at the scalar X direction resistivity curve, and it's showing us on one of the stations a large change here. This may be a static offset, and other things. We can do a Bostic section, which is a non-smooth Bostic section. So the typical EVAT section will correct for the static offset. Okay. So let's get to the meat of this and go to the actual inversion software. And there are two inversion software programs, and I'm going to concentrate on the Occam because I don't want to confuse the two different methods, although they are similar. Occam 2D. So what we're going to do in Occam 2D, after we've read in the data and edited the data, the basic steps are to rotate all of the stations to the profile line. We're going to define the TE and TM. And in general, TM is a magnetophorics term. We can assume that that is in the X direction. There are other more formal definitions, and the formal definition is the X dipoles are perpendicular to stripe. They're parallel to the profile direction, which is perpendicular to this geologic strike of the target. Many times you don't know the geologic strike of the target, so we're going to define the x direction as the rotated direction of the x dipoles, so EX. And TE will be the direction of the EY dipoles. And so, as I mentioned, we're going to edit the data, we're going to rotate the data into the profile direction, we're going to define TE and TM, and then we're going to go to the Occam inversion parameters to set those parameters. So let's do that. First thing we're going to do is we're going to go to Edit, and we're going to click on Rotate and set the TE-TM mode. And typically we're going to rotate it to the profile azimuth. So since the profile azimuth was defined as negative 21 degrees or 339 degrees on your full 360 degree compass, I'm going to click that, and we are going to define the X impedance, basically your EX direction, as TM. And that will automatically define TE as the Y direction. So I click on OK. So now I have edited the data. I've rotated the data. And I've defined the TE-TM mode. And now we go to the Occam. And the first thing you need to do before you can save the Occam file is click on Occam inversion parameters. Okay. The maximum column width and column growth factor and first row thickness and the vertical growth factor, these are going to define the mesh for the actual inversion. And we are going to use both TM and TE. And as I just explained, the TM will be the resistivity in the X direction along the profile line, and the resistivity in the Y direction, which is perpendicular to the profile line. And formal definition, if you know it, is perpendicular to strike, and you always want to set your X direction perpendicular to strike so you can see the target. Noise floor, leave that at 5%, that's fine. And you can leave the growth factor, horizontal growth factor. What that is when you're doing an inversion, you don't want edge effects. So you're going to add some data on the start and the end of the line because there is no data on either side of the start or the end of the line. And you need that to avoid the edge effect. First row thickness is exactly what it says. That is going to be the starting thickness of your first row. The vertical growth factor right now is 1.1. So every layer, as you go down in depth, is going to increase by an additional 10%, 110%. So if your first layer is 5 meters, your next layer will be 5.5 meters, The next layer after that will be an additional 10%, etc. And the initial resistivity is based on the resistivity of the data. And the number of iterations typically will be somewhere between 10 to 15. We will leave this at 10. And I am going to take off the static. If there is obvious static offset, and then you would want to invert it to correct for that static offset. There can be quite a bit of difference between static corrected and uncorrected. And we will do the static uncorrected at this point. Then I will click on OK. All right. The next thing I'm going to do is I am going to save the Emage2D files. And I need to define the folder that it's going to be saved in. And we're going to go to Emage Data. And of course, you're going to define whatever folder you choose. And I'm going to select that Emage Data folder. And then I'm going to give it the model name. Now, the trick on this is the model name is also going to create a subfolder to Emage Data in that same folder. So I will call this Emage Test X, whatever we decide to call it. Emage Test X. And now there is a quirk in this software that the model name does not like spaces in the name. So where you would normally put a space, I've just put a hyphen. Okay, so we've got that. And you'll notice that the Run Emage after exit is checked. That means when I click OK, it is immediately going to run the Emage exit. And what I'm going to do is I'm going to stop recording while it is running, because it will take several minutes. I don't want to waste your time just simply running it, simply doing the recording while I'm running. And I am going to click on OK. And if we were to watch this entire session, it would take several minutes. But fortunately, I have done this previously, so we can look at the end result. So what it's doing is running through. Misfit is a measure of how well the observed data matches the model data. And a very, very good data with almost perfect matching to the model will be a misfit of about 1.0. That is very unusual to get that sort of misfit. Anyhow, we're going to go ahead and wait for that. But I am going to hide this temporarily. And after the inversion is finished, what we'll do is we're going to open. We're going to retrieve the Occam model from that inversion. And I'm going to basically do one that I've already run. And I will just take the 10th iteration on that and open that. And okay. So you can see that there is quite a bit of difference in the Occam resistivity profile and the EMAP profile. We have got a strong conductor here and a moderately strong resistor at the surface. Right now we're looking a little over 500 meters, but we can change that. And the way that we do that, you can do that's to save the Occam. We won't bother doing that at this point. If I do a double right click or left click, it shows this color scale. This was the same scale that we saw in the EH5 Pro video. And it is the same method. We can change the scale. Right now it's going from 0 to 588. Let's say that our depth of interest was 700 meters, and we want to see a bit beyond that. So let's put on 800 meters. And okay. So now we're looking at a depth section of 800 meters. And if we were to look at the phosphate data, we can see that we are getting down fairly deep in many of these soundings. And let's change that so we can get a better view of this. So there's 100, 200, 300, 400, 500, 600. And in some of these we're getting down to 700 meters. We can write 2 here, there's 700. And so we can we're actually getting down to about 700 meters on this particular data set. And, but the inversion will extend it a bit deeper. Okay, and let's go back to well, I didn't save that Occam to the, we'll go back to Occam and just reread it. And as we did with the Bostic transform, you do your double click, and you can change both the depths and the color scale. Right now it's going from 8 to 61. We can go, let's say, go from 9 to 50. And of course, this does not change the data, it changes only the way that it's presented. Okay. But the one thing that does is brings up this resistor in the center of this profile. And you can see this profile went for about 600 meters. And that was based on the GPS reading of each one of the sites. Okay. So I just wanted to keep this very brief. We can also run this with the static correction. So we're going to do that also. So we're going to go to Occam and Occam Inversion Parameters. And we're going to go ahead and click on static. And okay, everything that has already been done previously is still there. And we will save it. Occam. Save Occam 2D files. And we're going to go to the same place. We'll put that in. We'll just put that in. Occam X. Dash static. Occam data. And we will call that Occam X dash static. And it still runs after exit. And again, it will go through several minutes of doing that. So, and the other one would have been done. We'll retrieve that other. Oh, Occam test X. What's the last one? Yeah, it's the same as the one I've done previously. And we're going to try Occam retrieve Occam model. And static and temp iteration and open. So here's corrected for static. It's basically the same. This area in here is different, and this anomalous is different. You don't want to do static unless it's very evident that there is a static offset. That, I believe, was explained in a previous training video. Okay, so we will enter this or end it now. Oh, this has a very good misfit of 1.0. So we will end this video training now. and we will discuss again once you have collected data, and we will review that data in another online session. Okay.